Welcome everybody to our next N3AS seminar of this lovely spring semester. And today we're very excited to hear from Joonas Nättilä from the Flatiron Institute and Columbia University, who will tell us about neutron star weather forecasting. Please, Joonas, take it away.
Thank you, and thank you for the invitation. So today I'm going to speak about this esoteric sounding title of neutron star weather forecasting, and I think my work is to try to convince you that this is not a crazy topic, but there's actually some kind of justification why we do this and why this is an important thing to study. And this is work done by collaboration with James Joe, who's in Brandeis now, and then Jack Skinner at JPL, and Bart Rippert and Elias Most, who are at Princeton in N3AS. So also feel free to add questions even on the go, and I'm happy to take and stop and explain stuff. So before going further, I just wanted to kind of get us started and just say that this is actually not something I do regularly. I don't do neutron star forecasting as my main thing, but I'm mostly interested in astrophysical plasmas in general, like non-thermal particle creation, plasma energization, and then focusing especially on these high-energy astrophysical objects like accretion flows around black holes, neutron stars, fast radio bursts, neutron star mergers, and magnetar bursts. So this whole neutron star weather forecasting was kind of an interesting collaboration with which started with mainly with James Joe, who is an geophysicist and really coming from the geophysical background of fluid dynamics, and me from the high energy side from understanding neutron stars. And we started to put these kind of pieces together and building a picture of what can the weather on so-called weather on neutron star look like. So I don't think this audience needs this introduction, but let me anyway go and dive right into this. So as you probably know, neutron stars have a structure. Typical neutron star has maybe radius of roughly 12 kilometers. It has a mass of 1.5 solar masses, ranging from maybe 1 to up to 2.2 solar masses. The spin changes from 1 millisecond 10 to the minus 3 all the way up to maybe 10-second periods. So the time to go around with one rotation for the star. And also the magnetic field changes vastly from 10 to the 8 all the way up to the 10 to the 15 Gauss magnetic field. So from very strong to very, very strong magnetic fields. And the whole business of why most people are very interested in neutron star is really related to the composition of their core. So we still don't know actually what is inside in the very deep layers of the neutron star core, which is supposedly a liquid neutron gas that then basically gives bulk of the size of the star and tells us how all of the properties of the star. But what we do know quite well at the moment is how the stuff on the top, on the so-called low density regions behave. So on top of this liquid crust, liquid core, we have a solid crust which is actually a degenerate electron gas, which crystallizes into a crystal lattice. So it's some kind of a stiff solid structure, and then sitting on top of that is so-called the neutron star ocean, and then even more diluted, there's an atmosphere on top of the star. So the atmosphere is a gaseous layer. Ocean is actually what we call a Coulomb liquid, with some sense resembling a liquid, like in generally a fluid, and then that whole thing sits on top of a solid crust of the neutron star. So from the kind of perspective of thinking now this in terms of geophysics and trying to kind of build up connections, what we can basically think is that we have a solid bottom, actually very similar to what we have on Earth. We also have a solid crust where we are all now standing on top of, and then on top of that there's a liquid ocean layer, and then when you go to higher densities, lower densities on top of the ocean, there's this liquid plasma gaseous atmosphere on the top. So the height of the atmosphere itself, this gaseous layer, is roughly 20 centimeters. This is now measuring from 10 to the 4 grams per cubic centimeter all the way up to maybe 10 to the minus 2 grams per cubic centimeter. And then this whole gaseous 20 centimeter layer is sitting on top of maybe half a 5 meter layer ocean, which is liquid. So these are actually kind of size scales that I think we can kind of comprehend. The 5 meters and then 20 centimeters of gaseous layer on the top. And then of course the laterally, like this whole thing is sitting on a sphere of roughly 10 kilometers. So it's an extremely thin layer of fluid sitting on the solid crust. So there's already actually here nice analog between Earth. Earth also has a solid crust, and then on top of the crust there's an ocean, and then on top of ocean we have our own atmosphere. So as we will actually go along, there will be quite a bit of interesting analogs, I think, even in our solar system that have that are from fluid dynamics perspective interestingly similar to us that neutron stars actually are. So now if we take a fluid, that fluid, like we typically know, will be balanced, meaning that it will be actually hydrostatically balanced, meaning that it's not going up or down. There will be an hydrostatic balance and gravity pulling everything down, and then the solid crust and the pressure gradient from that is basically balancing me from the below. So the fluid is kind of pinched on not moving up or down because of the huge gravity of the star. But the important point here is that the whole thing is balanced only like in up and down direction. It's unbalanced actually in a lateral direction. So the whole thing can move sideways, and there's nothing preventing from this fluid moving left or right, basically, in this picture. So that's, of course, we already know from all the dynamics of, let's say, Earth. If you go outside, there's also a fluid there, our own atmosphere, which can also move sideways, which is the wind. So even though the wind is not escaping anywhere, it's not going up or down significantly, it can still actually have strong streams going laterally along the surface of the star. So there's actually, in this picture, nothing preventing from the same happening on the neutron star. And the phenomena is, I think, closest kind of resemblance you can think is that if you have a bathtub and you put in a thin layer of fluid, yes, the fluid is not going up and down, but if you poke your finger on it, there will be actually waves excited on the surface. And these waves are typically more than so-called surface gravity waves. So we can, for example, calculate what is the equivalent of surface gravity wave speed on top of a neutron star, and or vice versa, what is the sound speed in the medium, and both turn out to be something like 10 to the 8 centimeters per second. So something quite fast, meaning that the information can propagate very fast laterally on the neutron star surface. And then, of course, from Earth, we already know that this is the kind of cause of the weather and climate eventually that we have on Earth. This whole layer is nothing preventing from it going left and right, and then that causes all of these interesting fluid motions that we call weather now on Earth. So something I'm not going to go into, but in a paper that we are preparing that should be out actually very soon, we come up with many different ways of exciting the layer. And actually, there turns out to be many ways of how you can perturb the surface layers of neutron stars. And I think that something that makes most sense for this discussion is, for example, to think about star quakes. So these are one of the most energetic phenomena happening at the star, where this solid crystal lattice basically yields, and instead of having an earthquake, you have basically a star quake type of phenomena where the crust impinges and then launches a perturbation into the ocean, and then you can basically tap into this energy, and then that energy can drive the motion of the fluid on the top. You can also envision much more different kinds of forcing mechanisms, for example, coming from accretion of the star, from a neighboring star, and so on. But I'm not going to go into very much detail into this. I'm just going to leave it here and say that there are actually many ways of putting motion into the fluid layer. So to start up, let's do a kind of warm up in 2D hydrodynamics. So this is a 2D Navier-Stokes equation telling us basically how the velocity vector v here evolves as a function of time. And then now I've written it actually in non-dimensional form, so that there's a nonlinear term here on the left-hand side, and then everything is balanced by a diffusion term on the right-hand side. And then you can see that with this notation, with using dimensionless parameters, there's a Reynolds number here as a divider, which is some kind of a value describing how strong the dissipation is going to be in the medium. So interestingly, if we plug in characteristic numbers of neutron star oceans into the Reynolds number, we end up with something humongous number like 10 to the 14, which is a very big number. If we kind of extrapolate from Earth context, we know already that Reynolds numbers of maybe around 3,000 start to be unstable for turbulence. So 10 to the 14 is actually plenty of scales for the medium to flow and become really turbulent. So for us, this is kind of already the first sign that probably that layer sitting at the top will actually be highly turbulent if you somehow put it into the motion. So in reality, what I'm doing is I'm actually not analyzing 2D Navier-Stokes. I'm going further and I'm analyzing the magnetohydrodynamic shallow water equations. This is something I'm not going to go into very much detail, but if you're familiar with this, this is a kind of a 2.5D equivalent of a 2D MHD system, where on top of nonlinearity, I also take into account the equation for evolving the height of the layer, and then equation for evolving the internal magnetic field of the system. And then it has same kind of diffusion terms for both B and velocity field, but there's also coupling between magnetic field and velocity, and there's importantly coupling between rotation of the system that you're sitting on. So it's actually this rotation that's very important to us, and we already know this from the whole context of many of the solar system planets, for example, that the rotation plays a very important role in shaping how the weather and the fluid moves on top of the sphere. So what I've done here is that now I've isolated and taken the velocity component of this 2D MHD shallow water system, and then I've highlighted the rotation term, which can be then written in a non-dimensional form using what is a so-called Rossby number, basically a ratio of nonlinear term to the rotation of Coriolis term. And then this is basically describing you how strong the effect of rotation is going to be in the medium. So this is one of the parameters that the geophysical fluid dynamicists like to make, basically to estimate already before doing any kind of simulation what to expect from the system. So if the Rossby number is very large, it means that this rotation term will be extremely tiny and rotation will not be important for the system. So, and vice versa, if Rossby number is very small, it means that the system will actually feel the Coriolis force and rotation strongly. And interestingly, it turns out that if you plug in the numbers realistic for neutron stars, you end up with Rossby numbers ranging from 1, meaning that they are kind of rotationally somewhat important, all the way up to 10 to the minus 3, meaning that they are actually heavily influenced by rotation. So I think this is already quite an interesting sign for us that not only is the layer going to be turbulent, but it's actually going to be somehow influenced by rotation. And then we know from like everyday phenomena also on Earth that when you have a rotating frame, and we are living on one of them on Earth that spins also around its axis, rotating systems have a tendency of creating vorticity in the system. So we encounter vorticity also in our own weather system by, for example, forming these hurricanes and cyclones that are this tendency of fluid basically to move, but not to go anywhere. So basically, instead of if you want to move but not go anywhere, what you do is you rotate in place. And this is what the vorticity is basically saying, that I have locally tendency for the fluid to rotate around itself. So a reality check that we can do is this crazy? I would argue that no. Actually, we can look at the recent pictures, for example, of the Juno mission flying on top of a Jupiter. This is an image of Jupiter polar cap done in the infrared band, and you actually see this beautiful 8 octet of vortices that we still don't actually understand fully what is the dynamics of these. But this kind of a beautiful example showing that solar system planets do have a tendency of creating these vortical structures out from the rotation of the system. So it's really an inherent feature of especially 2D fluids to create vorticity in the system. And then I'm not going to spend too much time on this, but we can go all the way back to the 80s and 90s, and I think we have quite a good handle now of how vorticity itself interacts, which is in some sense a higher order quantity for the 2D fluids to describe their dynamics. So there are two mechanisms how basically two vortices, rotational kind of, you can think of them as storms, can interact. So one of them is a vortex merger, where two vortices can merge and basically grow in size and become bigger, which is depicted here by a big vortex merging with a small one, going all the way from Yasuda's from 95 paper. And then there's an opposite mechanism called vortex filamentation, where you can think that there's a big vortex that's actually slightly elliptical, and that thing is wobbling, and then that wobbling causes it basically to lose and filament into these streams that then reconnect and snap and create you and give you tiny vortex on the top. So the main point here is that vortices, we've known this from the 80s nicely, that the vortices can both grow in size by merging, and then they can grow basically decay in size by emitting another small vortex by this filamentation method. So one last key ingredient that I think is important for understanding these systems from kind of very rough theoretical point of view is that these vortices can merge, but there's also the vortex merging direction is complex. So if you take in general a system living on top of a sphere, there will be the Coriolis force, which will be mainly acting on the equator. And then since you go along the poles towards more and more to the rotational pole of the star, you can see that the Coriolis force is actually decreasing for the system. So this means that we know that these systems have a tendency of experiencing, or vortices have a tendency of experiencing strong vortex dynamics, especially on the equator, and then this effect of vortices talking to each other gets weakened and suppressed when we go towards the poles of the stars. So interestingly, what this implies is that on the equator side, I can always prefer east-west direction, east-west directional mergers of the two vortices, whereas in the northwest direction, I statistically have less vortices interacting because of the decreasing Coriolis force. So the interesting kind of implication of this is that I favor basically vortices merging always in east-west direction, that you can beautifully see by when you merge 2 and 3 vortices together. What you start to do is you start to get what is called the jet streams. So instead of me and the fluid rotating around itself, it actually has a tendency to create these so-called streams or banded structures where the flow is actually going one way, for example, in some location going the opposite way. You can also calculate what would be the effective size scale of this phenomena. So this is basically what is also known as a Rhine scale, balancing basically roughly what is the distance that a structure can travel before it feels a Coriolis force and is strongly perturbed. And for neutron star case, especially for the fast rotators, this turns out to be something like 10 to the 5 centimeters, so 1 kilometer, which to us implies that since the neutron star's characteristic size of 10 kilometers, it means that there's a special region in the star of roughly 1 kilometer where you're expected to show strong east-west directional vortex mergers. So before going into the actual neutron stars, we can now again ask that, is this something crazy? And it's, I think that there's a very nice analog from Jupiter. Again, this is another Juno picture. And Jupiter, as we all know, is actually famous for showing this banding structure. So you can see that the Jupiter forms these beautiful bands, which actually we believe is forming from the same mechanism of having this preferred east-west directional vortices merging, and eventually those chains of or necklace of vortices goes all the way around the star and then builds these nice structures of bands that we know that are striping the whole Jupiter itself. And then occasionally you have these bigger vortices inside. For example, a good example is the red spot that we see in the Jupiter itself. So again, this jet streaming and banding as an effect is actually not so crazy to expect from geophysical fluid dynamical systems. So this has basically helped us now to build an intuition what to expect from these systems. So in reality, we are basically analyzing the systems both from the geophysical fluid dynamics, just using this empirical and already known kind of scaling analysis from the systems. But what we can also do, and what we are really doing, is simulations of this fluid dynamics in the system, because we actually want to also verify the actual nonlinear dynamics of this. So what I'm doing is I'm basically solving the MHD shallow water equations. They are, for those who are experts, they are actually casted into so-called vorticity current form because it's a little bit more conserving scheme. And then I'm solving those, with high resolution on top of a sphere with a spherical basis. So this as a method is actually very well understood and very kind of well developed all the way from the 90s, especially from geophysical fluid dynamics, where we want to do global simulations of Earth. So what we have been doing with James Joe is basically taking these existing tools and then really starting to port them towards the regime where the neutron stars are living. And then the prime requirement, especially for neutron stars, is that you need quite a high resolution to resolve all the important scales in the system. So we are using very high resolution runs with an equivalent of in a Gaussian grid of maybe 1000 by 2000 grids tessellating the sphere. So as my first test case, I'm going to present two test cases, basically rapidly rotating and slowly rotating neutron stars. So let me first argue what happens to maybe a more complex case of a rapidly rotating neutron star that I'm going to call a millisecond pulsar. So I'll take a neutron star with a period of 1 millisecond, 10 to the minus 3 seconds, and then I take my characteristic velocity to be roughly 1/10 of the surface gravity wave speed. This 1/10 is basically a safety factor for me, but there's also a higher description that these surface gravity waves have a tendency of spreading in the spectral space and with roughly a factor of 10. So we know from fluid dynamics that this is kind of a good estimate for the characteristic velocity. So gravity wave speed was 10 to the 8 centimeters. So I think as my characteristic velocity 10 to the 7 centimeters per second, traveling information laterally on top of the surface. So in this case, a millisecond pulsar would then end up with a Rossby number of 10 to the minus 3. And then this scale, so-called Rossby deformation scale, where the Coriolis force starts to strongly affect a trajectory of something flowing on top of it, is something like 10 to the 4 centimeters. So 0.1 kilometer in this case on top of the sphere. So basically from this we can now expect that rapidly rotating neutron stars millisecond pulsars should probably be rotationally dominant. They should feel the rotation strongly, and then they should have some kind of special scale of roughly 0.1, maybe 1 kilometer in size, which is the largest scale basically that my storm or a vortex can grow before it starts to feel the rotation strongly. So we've done these high resolution simulations. Here I'm showing you the millisecond pulsar. The map I'm showing on the right is the vorticity of the star. So this is vorticity can go both ways, either clockwise or anti-clockwise direction. And then it's a measure of how many rotations I go per second. This star is taken to have a thin layer on the top of roughly 500 centimeters. Spin period is, like I said, 10 to the minus 3 seconds. Magnetic field is 10 to the 8 Gauss. And you can see that we start now by imposing a high frequency variation on the surface. And then when I let the simulation run, you can start to see that these initial perturbations start to evolve, and you can see this vortex dynamics taking place in real time. So very quickly, you can start to see that the vortices start to grow in size. That's expected because more vortices have a tendency of so-called inverse cascading to larger scales. So we can start to see bigger and bigger vortices or storms on top of the star in the ocean and atmospheric layers. But then also you can start to see that there quickly starts to be a tendency of creating these east-west directed flows because of this Coriolis force becoming weaker on the poles of the star. And as we expected or estimated before, the number of this banding structure should be something like a 1 kilometer roughly in size, which you can kind of by eyeballing see that there's this 1 kilometer band forming on the equator of the star. So as one of my first kind of predictions, I would say that it's very likely then that the millisecond pulsars, being fast rotators, they will actually start to look something like this. So they are this kind of weird combination of Jupiter forming banding at the equator, and then they form these more stable vortices or storms on the poles that cannot merge. So I think this is already quite interesting as a resultant implication, because we typically think of neutron star surfaces as something very boring and flat. So my second case is going to be then a slowly rotating star. And those are typically a little bit more tricky because the millisecond pulsars are typically so-called recycled pulsars, which have a low magnetic field of 10 to the 8 Gauss, whereas a regular strongly magnetized neutron star, for example, those measured by the NICER mission, where they try to measure the size of the star, they are typically more strongly magnetized systems with maybe characteristic magnetic fields of 10 to the 12 Gauss fields. So the strong magnetic field here will then actually magnetize the layer, and hence for me the need to actually solve the MHD shallow water equations with emphasis on the magneto part of the system. So this magnetic field also then introduces another characteristic size scale of the system, velocity scale into the system, so-called alpha and speed, which also turns out to be for 10 to the 12 Gauss systems on somewhere on the bottom of the ocean of the order of 10 to the 8 centimeters per second. So then the ratio basically of my characteristic velocity that I'm going to inject, and then the magnetic field velocity, so-called plasma beta parameter, is going to be something like 0.1, meaning that the system starts to be magnetically dominated instead of being hydrodynamically dominated. So this is already one characteristic change in the system, so from going from millisecond pulsar with weak magnetic field to radio pulsars with strong magnetic field. But it's actually quite interesting that for these systems, you can analytically also look from the equations that where in the hydrodynamic system, we have found the quantity that is dynamic is the vorticity. In mathematical form, this is the curl of velocity field. We actually see that the role of vorticity is taken by the electric current, which is now the vorticity of the magnetic field. And you can kind of, the zeroth order already mentally flip what we had for vorticity by basically what we have now with electric current. And you should expect same kind of dynamics for the current that we had for vorticity. The big difference here is that if you look at the equation for magnetic field, which is on the bottom, it looks very similar to what we have for velocity field, but the only key difference is that there is no rotational force. So the magnetic field, while in the equation form actually looks very similar to the velocity field, will not feel the Coriolis force. So only the fluid motion itself, the motion of the fluid can feel Coriolis force. Magnetic field itself is ignorant of the Coriolis force. So basically, the zeroth order, we can from here then estimate that yes, we expect same kind of vertical structures, but now not in vorticity, but in current. But then the current will not know anything about the rotating system, even if it's fastly rotating. So the last experiment I'm going to present you with is now then a radio pulsar, same kind of setup. Now, instead of showing you the vorticity, I'm showing you the electric current. This is actually the current pointing along the surface of the star. And then the layer is strongly magnetized. So we basically expect that the instead of having this vortex dynamics, we will have current dynamics, sometimes also known as plasmoid dynamics. So very quickly you start to see that we see same kind of behavior. It formed the motions on the top of the neutron star surface have this tendency to create these vertical current structures, or what I call current spikes. But then the key difference from before is that you will quickly see is that there's no preferred direction, especially in the east-west direction, because this vortices, the magnetic field doesn't know anything about the rotation of the star. So instead of then creating these hotspots or circular storms of fluid motion, we actually have a tendency for strongly magnetized neutron stars to create these current spikes, but the current spikes are then expected to be more uniformly distributed along the surface that you now start to see. Like we have similar kind of spots going from the equator all the way up to the poles. So as something kind of as a teaser, we've been doing also ray tracing simulations of basically trying to answer the long-lasting question of how do neutron stars actually look like. So we took one of these hydrodynamic simulations we had that showed this formation of jets on the equator, and this is a preliminary result showing you the ray tracing, how we would actually see in curved space-time the neutron star looking. So you can kind of see that the system rotates, and in the equator it has this tendency of showing these more elongated stripes because of the jet streams, and then on poles we start to see this spotted behavior. So I think so far this is kind of the closest we can actually expect what neutron star will in reality look like. So this division of between stripy equators and spotty poles, and then of course depending on magnetization, you can suppress this stripiness on top of in the equator of the star. So I'll finish my presentation here and basically leave you with my conclusions in the visual form, showing you what I predict the millisecond pulsars will reality look like. Low magnetization but fast rotator, so we'll have these jet streams on the equators, and then a slowly rotating or strongly magnetized neutron star will then have these current spikes on that is shown on the right panel. So I'll thank you for your attention, and if you have any questions, I'm happy to answer them. Thank you.
Great, thank you, Joonas, for that very interesting talk. If you have a question you'd like to ask, please raise your hand digitally. And I do see a digital hand from Susan. Please go ahead, Susan.
Oh, I have many questions, but I would just like particularly to ask about the thickness of the banded feature that we saw both. We saw it on Jupiter, we see it on your left-hand side millisecond pulsar. And what sets its thickness? I mean, as it presents in the two-dimensional projection?
The thickness, though, the width of the banding region is set by so-called Rhine scale, which is the measure of the gradient of the Coriolis force, how fast it weakens towards the pole. So I wrote the Rhine scale.
Like the thickness of the jet stream on our Earth? That somehow.
Yes,
okay.
There is a similar analog. I think I have a Rhine scale written here, sometimes called a L beta scale, which is the characteristic velocity, characteristic size of the system, and then the rotation Coriolis parameter of the system, omega. And you're exactly right that we also see the same thing in Earth. I think in Earth, you end up with something like 100 kilometers in size. They are sometimes called these, I think, traveling jet streams or something that I think there's a trivia that Columbus used these jet streams to get into America.
Oh, that's very interesting. Okay, I can't comment on that, but that's great. Thank you so much.
Next, I see a question from Alan Calder. Please unmute yourself and ask your question.
Yep, thanks. Have you thought about how these dynamics would affect the case of an accreting system that might produce an X-ray burst?
Yes, so that's an excellent question. Kind of that's on the end goal that we're aiming at, because the accreting systems are also way more complex, because on top of showing lateral motions in the background, they also have this active phenomena of thermonuclear burning happening locally as a spot. So that's something we definitely have on our radar. But the thing we started now was really to ask the zeroth order question, that how does it look even without any active regions burning or causing any asymmetry? How do you expect the surface to look just in a quasi-stationary state?
Sure. But if you get things like hot spots, I can imagine very quickly that would change the dynamics. Thank you.
Yes. And the interesting point here is, for example, what would be the interaction of those hot spots with the existing vortices already in the ocean? Because these ones, for example, the spots you see here, they have a vorticity of roughly 500 per second, meaning that the spot goes around itself 500 times per second. So those are quite intense storms actually on the surface of the star.
Very interesting. Thank you.
I see a question from Wick. Please go ahead.
Yeah, I just wondered about energy transport through this ocean. I mean, especially if you had a millisecond pulsar that was young and cooling rapidly, is there, how does that influence the weather?
Yeah, so there will definitely be also kind of lateral motions. So I think to zeroth order, you can think that the neutron star is really sitting on a solid crust. And like you said, the millisecond pulsars, especially, they are accreting. So they can, for example, have so-called pycnonuclear reactions sitting on the crust, which gives you kind of static permanent heating from burning of some fusioning basically material, which will of course release some of its energy. I think the zeroth order, for example, the question is that do we expect convective motions, where you basically would actually break the hydrostatic balance. And I think that we don't expect the convective motions in typical neutron star parameters, maybe during an X-ray burst because it's energetic enough and if it happens deep enough. But in general case, I think the picture is more diffusive, that if you release some heat from the below, then there will be motions that take it and transport it to sideways to some other region, similar to, for example, that the ocean is doing on top of Earth.
Good, thanks.
Do we have another question from Susan?
Oh, thank you very much. I was very curious. Our underlying crust model is something that's very smooth. Does it have any elevation at all? Because I was thinking you were talking about shallow water wave theory, and I'm
Yes.
thinking if I have tilts, then I have maybe the conditions to get solitary wave behavior, and maybe
Yes.
that would make the dynamics very interesting. I was wondering if you might have
Yes.
any comment about that.
Yes, excellent point. So you're kind of predicting all of our future research questions. So the locally the crust will be extremely smooth. This is already known because people have looked, for example, if you can get gravitational wave signals from a mountain on top of a neutron star. So typical zero order knowledge is that neutron star cannot have the crust cannot have a mountain more than maybe a fraction of a millimeter, so which is already actually a huge mountain for a neutron star because of the large gravity. But how you can actually create a large scale topological features like we have on Earth, we have mountains, we have sea bottom varying, which will actually affect the flow very interestingly, is if you make the star rotate fast enough, because then even the solid crust is actually yielding and making the star slightly oblate. So from the perspective of the fluid dynamics, basically, then you will see a hill on the equator, which is a very weird setup of having the fluid to basically slide down from the equator towards the pole, which also actually enhances, and it's one way of creating circular motion in the star. So there you have then this global hill region on the equator. Typical changes are actually minuscule, but the changes in the gravity is still effective of this working, functioning as a topological feature for the waves. And this can, like you alluded to, can cause all kinds of interesting phenomena like waves dispersing from this gradient and so on, and pushing the fluid into motion when it slides along this hill and so on.
So I think that's very interesting. I don't know how it would have impact on this eventual study of wanting to understand accreting matter and how we interpret X-rays for the properties of the neutron star. But I think it's a fascinating point. So thank
I
you.
would think that in general as a more kind of second order question, because I think the flow will be in some sense, neutron stars are quite close to being spherical. So this is I think zero order picture is this, but then the corrections that we can start to add, we can start to correct for all kinds of phenomena. Similar to Earth, we can correct for mountains and topology set by the mountain ridges and so on, but they are not the dominant drivers of dynamics.
Thank you.
Do we have any further questions for Joonas?
I'm also happy to take, like, if you have questions that you come up, just send me an email and I'm happy to chat them.
Excellent. Well, I don't see any hands for the time being, so let's thank our speaker again.
Thank you.
Thanks, Joonas.